This is day 4 of our confidence intervals unit. Today we're going to talk a little bit more about comparing z-intervals and t-intervals. So just a little review about what confidence intervals are. We first of all use confidence intervals when we're making prediction about a population. So usually what this means is we have some sample data. We don't have the entire population information, but we have some sample data and we're trying to make a prediction about what the population is. So maybe I collect data about 100 likely voters in Michigan to make a prediction about how all of the voters in Michigan will vote. We never use confidence intervals when we know all of the population data. Because the confidence interval is used to make a prediction about the population, there's no need to predict anything about the population if we have all of the data. So the point of a confidence interval is using sample data to make a prediction. If we have all the data, we don't need to make a confidence interval. It's most effective, however, when your sample size is large. Like a lot of things we've learned about in stats, the larger the sample size, typically the more precise our data is going to be. We spent the first few days of this unit talking about the one sample z-interval. A reminder that we use a z-interval when we know sigma, the population standard deviation. We use a one sample t-interval when we don't know sigma, but we know s. Again, if we know both of those values, use a one sample z-interval. As long as you know sigma, use a z-interval. If we don't know sigma, use this t-interval, especially if we know what s is equal to. So throughout this class, we've talked a lot about the standard normal curve. The standard normal curve is sometimes known as a z-distribution, and we're referring to this top graph, this bell curve that reaches its highest point here, and actually as it progresses to the right and left, it actually sweeps down kind of to the lowest of these 4 different curves that are shown here. That graph is called the standard normal curve. It's also known as the z-distribution. It's interesting, if you're working with a t-interval, there are several t-distributions or t-curves. So there's one z-curve, which we have all that information on table A. That's referring to that graph. But if you're using a t-interval, there's basically a different curve for any sample size that you're working with. Specifically, as the t-distribution, what happens is as your sample size or your degrees of freedom increase, the t-distribution looks more and more like this z-distribution. So if you have a small sample size, let's say 2, the degrees of freedom would be 1, 2 minus 1 is 1, and you'd be talking about this very shallow looking graph right here. But as our sample size increases to 5 or 6 to 21 to 31 and our degrees of freedom bump all the way up to 30, by the time where our sample size starts to get big, it starts to resemble the z-curve. So what happens to the t-distribution as n gets bigger and bigger? It looks more and more like the z-curve, the standard normal curve. And by that we mean that the graph becomes taller in the middle and there's less area in the tail of the graph. The tail of the graph sinks lower as you head out to values like 2 and 3. When we start talking about characteristics of the t-distribution, we're talking about any of these curves that you see here, and they all look pretty similar to the standard normal curve. So that means as far as the shape goes, the shape is bell-shaped, it's symmetric, single-peaked. Another word for variability is spread. You'll notice that the t-distributions seem to be more spread out than the z-distribution. That means it seems like the graph goes out wider. So for variability, a t-distribution has more variability than a z-distribution. Degrees of freedom are still found by taking n minus 1. If we consider the equation for the one sample t-interval, which is x bar plus or minus t star times s over the square root of n, then the margin of error is the stuff after the plus or minus sign. So the margin of error is t star times s over the square root of n. The standard error is the stuff after the t star, so the standard error in this problem would be s over the square root of n. And a reminder from yesterday, when you're actually carrying out the confidence interval, there are 2 conditions we'll check for using a t-distribution. First, an SRS was taken or a random sample was taken. And secondly, the population is normally distributed, or the sample size is large, or the normal probability plot is approximately linear, so it is not unreasonable to assume the population is normally distributed. So let's take a look at the problem on the back side of the worksheet. This is another example of a confidence interval from the 2013 AP Statistics exam. It reads, an environmental group conducted a study to determine whether crows in a certain region were ingesting food containing unhealthy levels of lead. A biologist classified lead levels greater than 6 parts per million as unhealthy. The lead levels of a random sample of 23 crows in the region were measured and recorded. The data are shown in the stem plot below. You'll notice that in the stem plot, they're written as decimals, so 2/8 represents 2.8 instead of 28. We're going to skip part A and move on to part B. It says the mean lead level of the 23 crows in the sample was 4.9 ppm, and the standard deviation was 1.1 ppm. Construct and interpret a 95% confidence interval for the mean level of crows in the region. And there is a typo in your worksheet. It should actually say mean lead level. Otherwise, it means it sounds like it's talking about the mean number of crows. It should be the mean lead level of crows in the region. So when we do a confidence interval, the first step is to name the procedure, the parameter, and the population. The procedure we're going to work with here is going to be a one-sample t-interval. And the reason we're using a one-sample t-interval is where it talks about the standard deviation. The mean lead level of the 23 crows in the sample was 4.9 and the standard deviation was 1.1. So the mean of the sample, or the sample mean, is 4.9. The sample standard deviation is 1.1. So this is S. They don't tell us sigma. We're going to be using a one sample t-interval because we don't know the population standard deviation. The parameter. We've mentioned the parameter we're using is mu. Mu is the mean. And in the problem several times it talks about means. In the question, the mean lead level of the crows. Construct and interpret a confidence interval for the mean lead level. So mu is the mean lead level. The population. Look for the sample size. That should help you with the population. Twice it talks about a sample of 23 crows in the region, or 23 crows. Our population is not going to be 23 crows. It's going to be all crows, or all crows in the region. I don't think it's necessary to put in the region. If you do, I think it's a little bit better answer. But this sentence should address procedure, one sample t-interval, parameter, mu is the mean lead level, and the population, all crows. Now we can move on to our second step. In our second step, we check conditions. So 2 keywords we're looking for. The first condition, we're looking for random. Do we have a random sample? Second condition, do we have normal? Do we have a normal set of data? So in the reading, if you go to the third sentence, it does say that lead levels of a random sample of 23 crows were measured and recorded. We do have a random sample. So if you want to say a random sample was taken, that's fine. Or if you'd like to plagiarize the line that talks about this random sample, you can do that by basically repeating what's written here. The lead levels of a random sample of crows were measured and recorded. You don't have to write both sentences. As long as you have one of those things, we're good. The second thing we're looking for is to see if our population comes from a normal distribution. And in the reading, it doesn't say anything about normal. So part 2, do we have a large sample size? 23 crows, it's not bigger than 30. Not a large sample size. Option 3, take a look at the graph. Now you could plug these numbers into a normal probability plot. However, the numbers are already graphed. They're graphed on a stem plot. And if you rotate this stem plot 90 degrees, what you kind of see is a graph that does look approximately normal. If you were to kind of imagine putting like a little bit of a bell curve over this, you could kind of see, taller bars are kind of in the middle, smaller bars in the end. This data does look pretty normal looking. So we're going to make a sentence about that underneath here. And it'll say something like this. This graph is called a stem plot. So instead of using a normal probability plot, we're going to say the stem plot. This stem plot to me looks like it's approximately normal. So we're going to say the stem plot is approximately normal. And then the rest of the sentence should sound familiar. So it is not unreasonable to assume that the population is approximately normal. In the past, we'd said the normal probability plot is approximately linear. Whatever the graph is, if the graph kind of looks like it's making kind of normal looking data, then we can say it's not unreasonable to assume the population is approximately normal. Step 3, carry out the procedure. So we're using a one sample t-interval. I'm going to copy down the one sample t-interval formula again. It's not necessary to do this on step 3. I like to have it as a guide, but if you just want to start substituting numbers in, you can do that. It says the mean lead level of the 23 crows was 4.90 parts per million. So 4.90 is your mean of the sample, your sample mean. Plus or minus t star. To find t star, we need to know our degrees of freedom. Our degrees of freedom in this problem is our sample size, which is 23 crows minus 1. So if we do n minus 1 or 23 minus 1, we get 22. So to find t star, we're going to use 22 degrees of freedom, 95% confidence, and refer to table B. So if we go across the 22 row, 95% confidence, we find our t star, which is 2.074. S is our sample standard deviation. It says that the sample standard deviation is 1.1. And our sample size is 23. That's n. When we crunch out the smaller value in the interval, we get a value of 4.424. And when we hit second enter and replace the minus sign with a plus sign, we get the larger number in the interval, and that happens to be 5.376. If you rounded slightly differently, that's fine. Let's go to our final step. We always start this step with we are, whatever your confidence level is. In this case, 95% confident. That. Now we talk about what our parameter is. Mu is the mean lead level for all crows. So we're going to say we're 95% confident that the mean lead level. We always repeat what our parameter was. If you want to include the for all crows here, you can, or you can just say mean lead level is between the two numbers that we got in our confidence interval, 4.424 and 5.376. If you have units like parts per million, we include those here as well. And we've worked our way through another example of a one sample t-interval here.